All right, now we look through here to find some useful lemma. One of these looks good. It must be this one. So we'll rewrite by nat.add_cancel_r, or apply it, in H0. Good. So we didn't really even need the assert. We can just directly apply nat_add_cancel_r in H0. Now we can rewrite. We'll just do substitute O. Have you seen subs? Subs to O says, all right, rewrite by that equation O equals P everywhere, and then get rid of O. So that's useful. Now what? Now we can, I think we should probably swap N plus P. So we can rewrite by add commutes of N and P in H, except that, what's it really called? Okay, how do we find out what its name is? We do search about blank plus blank equals, actually, it's the same thing again. There it is, nat.addCom. Fine. Rewrite nat.addCom and P in H. Okay, we're making progress, and now there's going to be a cancellation theorem for less than or equal. And how do we find that? With search again. I think you can just say search instead of search about. And in fact, if you know that what you're looking for is a theorem that concludes with a particular form, you say search head. Otherwise, you're searching for theorems that might take that as a premise too. So these search commands are extremely useful in finding the lemma you need to prove something. And you can never remember the name of all those stupid lemmas. So even if you've been using coq for years, you still do this search. But let's try a different approach. The theory of linear integer arithmetic is decidable. And there's an algorithm called the omega test, invented in approximately 1992 by William Pugh, then of the University of Maryland, for checking whether, one formula equals another in linear integer arithmetic. What is linear integer arithmetic? It's got add, and it's got inequalities, and it's got multiplication by constants, preferably small constants. Okay, so why did Bill Pugh invent this? He was optimizing Fortran programs, and you need to check whether this array subscript in this iteration of the loop is going to be equal to that array subscript in that iteration of the loop, so you can swap the evaluation of these things. All right, but it's useful for other purposes too. For example, this proof goal is a proof goal in the theory of linear integer arithmetic. So we will apply omega. Omega is a tactic built into coq, implemented in OCaml, I guess, that applies Pugh's omega test algorithm and produces a proof witness in coq. What is a proof witness? Well, you heard about that a little bit this morning. So let me give you another example. Very simple. For all x, y, x less than y implies, I'll do an even simpler example. X, y, x less than y implies x less than y plus 1. Okay, so really, you could do this in like 2 lemma applications, but your time is valuable. So I'm going to prove this by the theory of linear integer arithmetic. I think I need to say intros first. Okay? Often I will prove that 5 is greater than 3 by applying the theory of linear integer arithmetic. Because why not? Otherwise you have to remember the name of some lemma or whatever. Okay? So omega. And you can thank Bill Pugh. All right. Here are some more tactics for proof automation. If I have a hypothesis above the line that I know will not be useful anymore in my current proof goal, then I can get rid of it by saying clear. Clear H clears a hypothesis. Clear X clears a variable, right? You can only clear a variable if it's not in current use. But when I have a lot of things above the line and I'm trying to figure out how to possibly make progress in a complicated thing below the line, if I can conclude that something above the line is not useful, I'll get rid of it so it won't distract me. This is a useful way to proceed. And by the way, if you say clear minus, let's say, H1, H2, that gets rid of everything except H1 and H2. So if you think, okay, everything I have below the line should be provable just from these two facts, then you do clear minus, and it strips away all the complicated gunk that would just distract you. Subst, I showed you subst already. Quite useful. It basically does rewrite below the line, rewrite above the line, and then it does a clear of the now sort of useless x equals whatever when that's the only mention of x in your whole proof goal. Okay, that's subst x. Subst says do that for all the variables you can. Okay. You can rename a variable or rename a hypothesis. This can be useful if you did some sort of inversion or some other tactic that introduced variable names automatically and you don't like its variable names. Now, a more disciplined way of doing this would be to do the destruct with the extra square bracket parameters that give names. But if we were disciplined, we wouldn't need proof assistants to check our work, would we? Okay. Assumption says there is some hypothesis above the line, call it H7, where apply H7 would solve the goal. All right? But I don't want to look up and figure out what its name is. So I just say assumption. It doesn't seem like this saves you much work. You could just say apply H7, and that's fewer characters. But the point is, when you're writing proof automation scripts, then it's not always H7. It might be different hypotheses in different cases of your destruct. So assumption is very useful in proof automation. Okay, contradiction. If you have H colon false above the line, that solves the goal. Or if you have H colon foo, where foo simplifies to false, or is beta eta equivalent to false, right? So, or if you have two things above the line and one is the negation of the other, right? Contradiction, quite useful. And now, constructor. So what you have below the line is a proof goal in some inductive proposition. And so how do you solve those? You might say left, or you might say right, but left or right are just short for apply, this constructor or apply that constructor. Maybe you have an inductive proposition with 6 cases, and how do you solve that? You could apply the name of one of its 6 cases. But I can never remember those names. So constructor says, we know what inductive proposition, what type that inductive proposition is, so look up the names of its constructors and see if if one of them will solve the goal. Or at least make progress. See if one of them applies. So constructor is useful when you're too lazy to remember the names of your constructors, or in proof automation where you've gotten to a certain point and it might be different constructors that apply in different cases. Now there is a danger in using constructor. It could be there are 2 different constructors of your inductive proposition that can make progress, but only one of them leads to a correct proof. So constructor by itself can turn a provable goal into an unprovable goal, and you do have to watch out for that. Okay, So let's change the subject. That was proof automation for a little while. Let's go back now to operational semantics. And when we write operational semantics, let me use the board for a second. I think I have to raise the screen from the device. And if I raise the screen from the device, it'll say, oh, you meant to turn off the projector, which I didn't. So I won't use the screen. Who has ever seen operational semantic notation of the form E double down arrow V, which means E evaluates to V? Okay, so that's what we're doing here. It's a relation, E evaluates to V, because for some E, there is no V such that E evaluates to V. So it's a relation between E and V. We know that in coq, or in logic, a relation is expressed as a function from E to V to prop. So this is, A eval R is an inductive relation. And when you've seen E double down arrow V, it's presented as a bunch of inference rules, different ways of proving it. And you're guaranteed that whenever E evaluates to V, it must be by one of these inference rules. There are no other ways of proving that E evaluates to V. And that allows you to do inversion over E evaluates to V. Well, you've seen inversion over inductive propositions in coq. It's exactly the same. All right, so here we are. Here's E double down arrow V. It's called A eval R. A for arithmetic, eval for evaluation, R for relation. It's the arithmetic evaluation relation. It takes an arithmetic expression and it relates it to a natural number. And we have four cases. A eval R relates A num of n to the value n. A eval R relates A plus E1, E2 to the number N1 plus N2 if you have above the line of your inference rule that E1 down arrow N1 and E2 down arrow N2. And similarly for minus and mult, but here we have the arithmetic subtraction and the arithmetic multiplication. And here's double down arrow in ASCII. Well, it's the best we can do. Actually, the best we can do would be 2 vertical bars. That would at least be down, but 2 vertical bars is already taken. So it's the second best we can do. It's not very good, actually. When you see these 2 backslashes, your mind should say double down arrow, right? Because that's what we're talking about here. Okay, so that's the inductive definition of the semantic relation for big step expression evaluation in structural operational semantics. All right. Some people are unhappy that in your definition of double down arrow, you don't get to use the fancy double down arrow notation. Hold on a minute. So we define this inductive relation A eval R, and then we define fancy notation, but we already had to 1, 2, 3, 4, 5, like 9 times, 10 times use the word A eval R. And this bothers some people. Doesn't bother me. But for the people that it bothers, if you want to define your notation simultaneously to defining your inductive relation, you can do it this way. All right. What bothers me is using notation when a perfectly good word would do instead. Let me remark that these constructors have complicated names that one can never remember, which is why that constructor tactic is so useful. Okay, now, what's next? Oh yes, when people do this in LaTeX, they use a double down arrow and they use a bunch of inference rules. But most of you knew that already. And the ones that didn't know it already, Well, read the comments in the text and read a popple paper and you'll see some double down arrows. Okay, now, let's do the quiz. With our digital response devices, we need to prove that A of L R relates this expression to 0. And which of the rules of the inductive definition of the proposition, the relation, are needed here? All right, well, I see a bunch of answers that I think are right anyway. Since you've got to evaluate numbers, you'll certainly need the num, the EA num constructor, and since you've got to evaluate this plus, you'll need the EA plus constructor, and since you've got to evaluate the mult, you'll need this constructor, so you need all these three, and there is no minus in this expression, so you won't need the minus, and therefore this is the set that you need. All right. Here are the double down arrow rules for Boolean expression evaluation. That B true evaluates to true. That B, Q, E1, E2 evaluates to B if E1 evaluates to N1 and E2 evaluates to N2, and then the Boolean equality of N1 and N2 evaluates to B, which is true or false. Okay? So we take this rule and we express it as a case in the inductive definition of the inductive relation B of Al R. And did I pass B of Al R already? No, not yet. Okay. Now, we had two different ways to do operational semantics. The one I've highlighted here with the A of Al function, I would call denotational semantics. And this one, the A of Al R, I would call big step operational semantics. And we can prove they're equivalent. So what does that mean? It means for all expressions A and values N, A of Al R relates A to N if and only if the A of Al function computes A to N. And it's proved by induction. And, well, okay, first there's a split, right? There's the forward direction. And let's go into the forward case. We have two choices what to do induction over above the line, A and N. What do you think? A looks more promising. Okay, so we do that induction. Now let's look at the backward case. Again, we have A and N. If we do induction on A, let's do induction on A. All right, first case is easy. All right, that was easy. Second case, did I show you E constructor yet? Well, if I say constructor here, it'll say, well, what will it say? Oh, that's no good. Let's apply EA plus. Is that what it's called? Oh, the A plus in its conclusion wants something on the right-hand side of the form something plus something.